Welcome to our comprehensive guide on PySpark. PySpark is the Python API for Apache Spark, a powerful open-source engine designed for big data processing and analytics. With PySpark, you can leverage Spark's robust features directly from Python, making it accessible for data scientists and engineers alike. In this video, we'll explore what PySpark is, its core characteristics, and how it empowers you to process massive datasets efficiently. Whether you're new to big data or looking to expand your toolkit, PySpark offers a flexible and scalable solution for distributed computing. Let's dive in and see how PySpark can transform your data workflows. PySpark stands out for several reasons. It abstracts away the complexity of managing individual worker nodes and networks, allowing users to focus on their data tasks. The Spark API in PySpark provides a rich set of functions for data manipulation, machine learning, and streaming. Built on the MapReduce model, PySpark lets you define map and reduce functions for parallel data processing. Communication between nodes is implicit, so you don't need to worry about low-level networking. These features make PySpark a user-friendly yet powerful tool for handling large-scale data. PySpark offers many advantages. It's simple to use, supports parallelized code, and provides robust error handling. With inbuilt machine learning algorithms and extensive Python library support, it's a favorite among data scientists. However, there are some drawbacks. Expressing certain problems in the MapReduce model can be challenging. PySpark is generally slower than Scala, Spark's native language, and its streaming API is less mature. Also, PySpark's abstractions prevent modification of Spark's internal functions, so Scala is preferred for low-level customizations. At the heart of every PySpark application is the Spark context. This is the entry point to Spark's core functionality and represents the connection to a Spark cluster. With Spark context, you can create RDDs, resilient distributed datasets, and broadcast variables across the cluster. It's the foundation for all distributed operations in PySpark. By initializing Spark context, you unlock the ability to process data in parallel across multiple nodes, making your computations both scalable and efficient. Spark files in PySpark are essential for managing external files within your Spark application. They allow you to add files to your Spark job using the SC, add file, method and retrieve their paths with Spark files get. This is especially useful when your tasks require access to configuration files, data files, or scripts distributed across the cluster. By leveraging Spark files, you ensure that all nodes in your cluster have access to the necessary resources, streamlining distributed processing. Realization is a key aspect of performance tuning in PySpark. When data is sent over the network or stored on disk, it must be serialized. PySpark supports two main serializers, Pickle Serializer and Marshall Serializer. Pickle Serializer can handle almost any Python object, making it versatile but sometimes slower. Marshall Serializer is faster but supports only limited types. Choosing the right serializer can significantly impact your application's speed and efficiency, especially when dealing with large datasets. RDDs, or resilient distributed datasets, are the fundamental building blocks in PySpark. They represent immutable collections of objects that can be processed in parallel across a cluster. RDDs are fault-tolerant, meaning if a node fails, the data can be recovered automatically. You can perform transformations like map, filter, and group by to create new RDDs, and actions like count or collect to retrieve results. This design enables efficient, reliable, and scalable data processing. Transformations and actions are two core concepts when working with RDDs. Transformations, such as map or filter, create new RDDs from existing ones without immediately executing them. Actions, like count or collect, trigger the actual computation and return results to the driver. This lazy evaluation model allows Spark to optimize execution plans and improve performance. By chaining transformations and executing actions only when needed, you can efficiently process large datasets. PySpark supports multiple cluster managers to allocate resources and manage distributed execution. The main types include standalone, Apache Mesos, Hadoop Yarn, Kubernetes, and local mode for development. The cluster manager assigns memory and CPU resources to worker nodes, ensuring efficient execution of Spark jobs. Choosing the right cluster manager depends on your infrastructure and scalability needs, but PySpark's flexibility makes it suitable for a wide range of environments. PySpark RDDs offer several advantages for big data processing. They support in-memory computation, which speeds up data processing by avoiding repeated disk reads. RDDs are immutable, ensuring data consistency and enabling safe parallel operations. Their fault tolerance means that if a partition is lost, it can be recomputed from the original data. RDDs also support lazy evaluation and automatic partitioning, making them both efficient and reliable for distributed tasks. Common question is whether PySpark is faster than Pandas. The answer lies in PySpark's ability to execute operations in parallel across multiple cores and machines, while Pandas runs on a single machine. For large datasets, PySpark's distributed processing offers significant speed advantages, making it the preferred choice for big data analytics. However, for small to medium datasets, Pandas remains a convenient and efficient tool. PySpark dataframes are distributed collections of data organized into named columns, similar to tables in relational databases. They provide better optimization and performance compared to R or Python dataframes. With dataframes, you can perform SQL-like operations, benefit from Spark's Catalyst optimizer, and handle large-scale structured data efficiently. This makes dataframes a powerful abstraction for both data manipulation and analytics. Spark Session is the unified entry point for all PySpark functionalities, replacing Spark Context since version 2. It allows you to work with RDDs, dataframes, and datasets using a single API. Spark Session also consolidates SQL context, streaming context, and Hive context, simplifying your codebase. By creating a Spark Session, you can access all of Spark's features in a consistent and streamlined way, making development more efficient. Spark supports two types of shared variables: broadcast variables and accumulators. Broadcast variables are read-only and distributed to all nodes, making them ideal for data lookups. Accumulators are used for aggregating information, such as counters or sums, across tasks. These shared variables solve the challenge of reusing and sharing data across different tasks in a distributed environment, improving both performance and code clarity. PySpark UDFs, or user-defined functions, allow you to extend PySpark's capabilities by writing custom Python functions and applying them to data frames. You simply define a Python function, register it as a UDF, and use it within your data frame operations. UDFs are especially useful when built-in functions don't meet your requirements, enabling you to implement custom logic directly in your data pipelines. PySpark is widely used across industries for big data analytics. In media streaming, companies like Netflix use Spark for real-time recommendations. Financial institutions leverage Spark for customer segmentation, risk assessment, and fraud detection. Healthcare providers analyze patient records and perform genome sequencing with Spark. The travel industry, such as TripAdvisor, uses Spark for personalized recommendations, while retail giants like Alibaba analyze petabytes of data for targeted advertising and customer experience optimization. Spark follows a master-slave architecture, where the master node is called the driver and the slave nodes are workers. The driver creates the Spark context, which manages the application and distributes tasks to workers. Cluster managers allocate resources like memory and CPU to workers, ensuring efficient execution. This architecture enables PySpark to scale seamlessly from a single machine to thousands of nodes, handling massive datasets with ease. DAG Scheduler is a crucial component in Spark's execution engine. DAG stands for Directed Acyclic Graph, which represents the lineage of transformations on RDDs. The DAG Scheduler breaks down jobs into stages and tasks, determines the optimal execution plan, and handles failures by recomputing lost output. By organizing computations as a DAG, Spark ensures efficient, fault-tolerant, and parallel execution of your data pipelines. Typical Spark workflow starts by creating input RDDs from external data sources. Next, you apply transformation operations like map or filter to generate new RDDs based on your business logic. If you need to reuse intermediate RDDs, you can persist them in memory. Finally, action operations like count or collect trigger the computation, launching parallel processing across the cluster. This workflow enables efficient and scalable data analysis. SparkConf is used to set configurations and parameters for running Spark applications. You can specify options like the master URL, application name, and other settings. SparkConf ensures your application runs with the desired resources and behaviors, whether on a local machine or a large cluster. Proper configuration is key to optimizing performance and resource utilization in your PySpark jobs. Spark offers multiple ways to create RDDs, such as using parallelize for in-memory collections text file, for reading files and whole text files, for key-value pairs. You can also create empty RDDs with or without partitions. For data frames, use the create dataframe method with data and schema. PySpark supports reading from various external sources like CSV, JSON, and Parquet, making it versatile for different data formats. PySpark SQL is a powerful module for processing structured data. You can create temporary tables from data frames and run SQL queries using familiar syntax like select, where, group by, and join. PySpark SQL enables you to combine the flexibility of Python with the expressiveness of SQL, making it easy to analyze and manipulate large datasets. This integration streamlines data workflows and enhances productivity. Joining data frames is a common operation in PySpark. You can use the join method to combine data from multiple data frames based on common columns. PySpark supports various join types, including inner, left, right, and full joins. You can also chain joins to merge multiple data frames, enabling complex data integration tasks. This flexibility makes PySpark ideal for building rich, multi-source analytics pipelines. PySpark streaming enables real-time data processing from sources like TCP sockets, Kafka, and file systems. You can use read stream, format, socket to stream data from a TCP socket, process it in real time, and output results to dashboards or databases. This capability is essential for applications that require immediate insights from continuous data flows, such as monitoring, alerting, and live analytics. PySpark's fault tolerance ensures that if an RDD partition is lost due to a node failure, it can be recomputed using the lineage of operations from the original dataset. This automatic recovery mechanism is a key reason why Spark is reliable for large-scale distributed processing. It minimizes data loss and downtime, allowing your applications to run smoothly even in the face of hardware failures.